Hello and welcome to Coffee and Control, the podcast where I find fascinating people from within the world of control and convince them to answer all of my questions. I'm your host, Lucy Hodgins, and today's guest is a senior lecturer at the University of Bristol. Now, I know I say this every episode, but I'm genuinely so excited about this guest. So earlier this year, my best friend Christian introduced me to a review paper that she wrote in collaboration with a bunch of other academics on robust control of quantum systems, and my mind was immediately blown. I was like, I need to make a podcast episode about this. People need to realise how cool this is. So fast forward about 6 months or so, I took a little trip across to Bristol to record this episode. Honestly, had the best time. This guest was so lovely, so enthusiastic. She showed me her lab where they're building really cool experimental systems. It was great. So because there is so much interesting stuff to explore in this field, I'm going to do 2 back-to-back episodes on quantum control. This episode is much more applications-based, and then next month I'm planning to follow up with a more theoretical episode with one of this guest's collaborators. So settle down, get ready to hear all about optimizing state transfer, combined robustness and performance metrics, energy landscape shaping, the many challenges faced when applying classical control to quantum systems, and why physicists and control theorists should really try to communicate better with each other, with my guest this month, Dr. Carrie Weidner.
I'm Carrie Weidner. I'm a senior lecturer at the University of Bristol in the Quantum Engineering Technologies labs. I'm trained as an experimental physicist. So I came up as an experimental cold atom physicist, and I still work primarily, I think, as an experimental atomic physicist. But I became interested in the control of quantum systems during my PhD. And during my postdoc, which I did at Aarhus University in Denmark, I managed to fall in with some very, very clever, very, very lovely control theorists and mathematicians and computer scientists, and got very interested in robust control of quantum systems.
I guess I'm kind of really interested in how you came into your research in control. So I guess most people working in control do undergrad in like either maths or kind of electrical engineering, but obviously you didn't. So yeah, I was kind of wondering like what parts of physics were you most interested in and how did that lead you to working in control?
Yeah, no, cool. So I did my bachelor's, master's, and PhD at the University of Colorado Boulder in the US. And I was one of the really lucky ones where like the moment I set foot on university campus, I was like, I want to be a physicist. Like I kind of knew that's what I wanted to do. But I had applied to the engineering school, basically, at the university, because they gave women more money, and I was also very poor. I grew up in Texas, and so it's actually, if you go to university outside of the state that you grew up in, you pay quite a bit more in tuition. So I knew I wanted to be a physicist, but I'd applied to the School of Engineering because they'd given me some scholarship money. And I was like, okay, well, what do I do? And so I had every intention to switch into the School of Arts and Sciences and do a double major in physics and chemistry, which is fairly common in the US to do that. And then I realized that the engineering school had an engineering physics major. And I was like, oh, well, I'll just do that. And I went along for a few years, and I ended up also double majoring in applied maths, but not like, I'm not a mathematician, like in the slightest. Basically, I tell people I got a dual degree in physics and MATLAB. And so afterwards, I wasn't entirely sure what to do. I kind of bounced around a little bit. I actually even like dropped out of my first PhD program. But I knew I wanted a PhD. I went back to the University of Colorado. I got quite lucky to get into the PhD program there. And I was doing experimental work. And the system that we were studying was one that was very difficult to solve analytically. And so in order to solve it, I was like, how am I supposed to do this? And I remembered that when I was an undergraduate, I was working in a lab, and the graduate student that I was working with had written a genetic algorithm to solve a problem. And I was like, well, I wonder if I could do that. So I wrote a genetic algorithm, and it worked, and it was solving the problem. And I was like, oh, this is really cool.
If you would like to know more about genetic algorithms and their possible applications, I'm going to link below an episode I recorded with Sabine Howard, talking about her use of genetic algorithms for control of swarm robotics.
And then as I kind of kept going, there were different like methods, right? And so I learned more methods that were sort of popular in the quantum control sphere. This Krotov method that had come up, and then also these sort of like Nelder-Mead style, but very optimal control. Not like I'm going to design the control, but I'm going to sort of play around in my search space and hope really hard that I find something. And I kind of tooled around a little bit with that, and I got really interested in it in general. But it wasn't until my postdoc that I was like, oh yes, control. And Sophie Shermer, who's a professor at Swansea, had come to Aarhus to visit and to do basically a PhD defense. And we just ended up having a meeting with her kind of off the cuff.
By the way, Sophie Shermer is the researcher doing more theoretical control that I plan to interview next month.
And the rest was history in a sense, because I started collaborating with her and Frank Longbine and Edmund Jonquier, who are at Cardiff and USC respectively. And we now also have Sean O'Neill, who is at West Point, which is the US Army's sort of university, which is interesting. And they're all like orders of magnitude cleverer than I am. But I'm an experimentalist and they're not. So that's sort of my how I kind of got into it is focusing a little bit more on how we could actually do control of quantum systems in like realistic ways. And it turns out the field doesn't hate that. So that's cool. Yeah.
Okay, can I ask you a few kind of questions about your PhD thesis?
Totally.
Okay, so your PhD was examining improving atom interferometry devices, as I understand it. So just a general overview, what is interferometry, kind of how does it work, why is it useful?
Yeah, so actually, like, laser interferometry, you can think about it like, and you can do this with anything that emits like a wave. Like you could, in principle, interfere water, right? If you have two waves traveling in opposite directions, there's this concept of constructive and destructive interference if the nodes and the troughs either overlap or are out of phase with one another. And so you can do the same with the laser, and this is kind of a really common canonical like way to torture undergraduates in physics, is that you give them a laser and a whole bunch of optics and you say, cool, make this laser interfere with itself. And so you need similar ingredients to do this in kind of any system, which is that you take the laser and you split it, which we can do actually just with an optic, and then you sort of let the light propagate, and then you use mirrors to steer it around, and then you operate that same splitter in reverse to recombine the light. So you have sort of splitting, propagation, usually some sort of reflection or reversal, so that things close in on themselves, and then you have this recombination step, and then you need to detect that. And so with laser light, you actually get a set of fringes of light and dark, light and dark, light and dark, and you can use this to back out interesting quantities. Like people use this for sensing gases and other things, like a change in the index of refraction of the air will cause these fringes to move around.
So Carrie has just described the classical light-based interferometry, but as she mentioned earlier, this works for anything that acts as a wave. So her thesis was focused on how to do this using atoms. Also, quick physics background. Carrie's about to mention using bosons, which are a type of subatomic particle along with fermions, but it turns out that atoms themselves can be classed as either bosonic or fermionic depending on how many subatomic particles they contain.
And one of the fun things about cold bosons, these are atoms that actually don't obey Pauli's exclusion principle like electrons do. So they like to just hang out together. And so if you make them cold enough, what you can do is you can have a potential that the atoms are sitting in, very much like a bowl. And you can think back to kind of classical physics. So, you could think of it as like a half pipe, for example, that a skateboarder is on or something. And where quantum mechanics comes in is that the energies that these atoms can have become quantized, as opposed to my skateboarder, which can have whatever energy they want. And so when these levels become quantized and you have bosons, as you make them colder and colder, more and more bosons will collect in this lowest energy state of the potential. And so then if you get your system, your sample of atoms, such that more of them are in the ground state really than anywhere else, they start to, it's condensing, and this is called the Bose-Einstein condensate. And then that these atoms are very much like the atomic analog to a laser. They actually have they're more like waves than like particles.
So, whilst I was in Cardiff, I got to see the lab that Carrie and her PhD students are creating to carry out their current experiments, which was very cool. So after the interview, we went down a few sets of stairs into this tiny little basement room, and I met Yolan and Deepak, who are two of her current PhD students, who were very nice, very kindly didn't object to me intruding in on their experiments. So most of the room was filled with these large tables, completely covered with different lenses and waveguides and beam splitters, all screwed down very precisely. In the corner of the table at the back, they had a big 46-watt laser covered in warning stickers. And then in the centre, there was this chamber with a camera mounted on the top. And inside, if you looked really closely, you could actually see the Bose-Einstein condensate glowing this kind of reddish light from where it was scattering the laser light directed on it, which was so cool. And Carrie was telling me that those atoms are the coldest point in the whole of Bristol, and that they got the temperature down to about 60 microkelvin, with the aim of eventually reaching a few hundred nanokelvin, which is wild.
There's this concept of a de Broglie wavelength, which is like the wave nature, this idea of wave-particle duality. You can calculate the de Broglie wavelength for anything based on sort of its mass and its temperature and et cetera. When you get these atoms cold, their de Broglie wavelengths are in the hundreds of nanometers, which is about, actually, if you do the calculations, the de Broglie wavelengths of these atoms end up being around the wavelength of green light. And so you can do the same things with these atoms, with these matter waves that you could do with light waves. And so you can split them apart and you can bring them back together and you can recombine them. What we did is we put these atoms into a sort of an ordered potential, which is an optical lattice. What you get when you actually take a laser beam and you reflect it back onto itself, it will interfere with itself. And we would exploit that. And so that actually looked a lot like an analog to a laser, a way to split a laser, this idea of a diffraction grating where a laser comes in and it reflects off and you can get these higher order modes. And it's very similar to what you see in the double slit experiment for electrons. You could do this with atoms. It was wild. And so basically what we did is we sort of figured out how we could jiggle around our light potential in order to drive the atoms from kind of their ground state to whatever state we wanted, where we were causing them to move in opposite directions and then reflecting them back and bringing them back together. And that was the problem that was really hard to solve analytically, except in the absolutely simplest of cases. And so that's why we had to start thinking about control.
So, talking more about control, what is the control objective? What are the control inputs? How do you kind of impact the system?
Yeah, no, that's a really, really good question. So what the type of control that we do in quantum control language is called state transfer. So you have an initial state that you start with, and you know what it is because you know that if you've done everything right in the lab, that your atoms start in the lowest energy state of their potential, the ground state. And then say, I want to split my atoms such that they start in the ground state and they end up having, say, equal and opposite momenta. So they sort of run away apart from each other. I can look at that in momentum space. So you can actually think of position space and momentum space. They're Fourier duals of one another. And so we actually would think in momentum space. And so we had our initial state, which we knew because we could do the calculations and we could actually do the experiment. We can measure these things. And then the state that I wanted, which was sort of half of the atoms moving with some quantized momentum and some other equal and opposite quantized momentum. And so it was a state transfer problem.
It's worth keeping in mind throughout this episode that this state transfer problem, where you're moving from the ground state to a final state within a certain time, is the objective of a large proportion of the work Carrie does, and also a lot of work in quantum physics more generally.
And then the control input was actually how much we jiggled this sort of this periodic potential of the laser reflecting back on itself. In the jargon, we call it an optical lattice. And so the sinusoidal potential that we have made, we change the phase so it would move back and forth. So we'd go from the state that we started with to the state that we wanted. And you can actually have time as a control input to try to do this as quickly as possible. But often I would just sort of set that. And we would design the controls such that the bandwidth is limited, because my experiment could only handle so much, right? I could only actually shake this thing so fast. And so instead of using sort of piecewise constant controls, we actually decompose things into a Fourier basis. But we had to smoothly turn things on and off, so I sort of thwopped an envelope on top of it. So which of course widened things out in Fourier space, but at least made it so that my experiment was less angry at me than it would have been otherwise.
You mentioned earlier kind of different approaches to optimization. Mm-hmm. So I think you mentioned genetic algorithm, Krotov, and then Crab method?
Yeah, this crab method, yeah.
Yeah. Could you explain a bit more about kind of how these work, what are the differences between them?
Yeah, so genetic algorithms are kind of fun because they're non-deterministic. There's like an intrinsic randomness in them. And you set up this like set of you call them genomes, or there's sort of varying levels of like weird biology misappropriation that happens here. And you try to have that like span the space. And your search space, for us, it was actually just a set of frequencies that we would modulate this thing at. And so we would sample this like crazily high dimensional search space. We did all of this to start with in simulation, but you could think about doing it in an experiment. And then we'd get a whole bunch of, our metric, for lack of a better term, was like, how well did the final state we got, the state we got at the end, overlap with the state we wanted. And so the whole point is you have to distill how good everything is down into one number. I think we occasionally added a penalty for like shaking really hard or shaking really fast or something. But at the end of the day, all we cared about was state we wanted close to state we got. And so you would do that and you would sort of evaluate the fitness of all of your little genomes. And then you'd have the two that were the best, and they'd stay and they'd propagate through to the next generation, which sort of enabled that your best solutions always persisted. And then you would usually kind of kill off some of your worst. And then everything that was left would kind of breed together. And so you'd mutate things a little bit, you'd kind of fiddle with things a little bit, or you'd swap around different parts of this quote unquote genome. And then you'd run it again, and you'd see, and like again, then you do the same thing ad nauseum. And this is fine. It works. Like that's one of the things about the genetic algorithm. Say what you will, it just works. But it might take ages. And on some problems, it did take ages. And so that was the genetic algorithm. And then just kind of thinking chronologically, actually, my PhD advisor went off and met with a fellow named Ronnie Kozloff, who's big in quantum control. And he came back and he was like, Ronnie was telling me about this method called the Krotov method. You should go learn about it. And that's when I learned that computational chemists are very intelligent. They write papers that are very difficult to understand. But eventually I sort of sussed out how this algorithm worked. And it's very computational. Like it's not one that you can implement in an experiment, at least as far as I can tell. Or nobody's done it yet. Because what you actually do is you time propagate your initial state forward. This is usually described by the Schrödinger equation, which describes most of quantum mechanics. And then you would take the projection of that state onto the final state you got, then propagate that state backward. And then I'm glossing over a lot of the details here, but then you would start looking at how that changed if you changed your control. So you'd be doing derivatives with respect to your control and all of this. But it's this whole idea of sort of back propagation that's very difficult to do in the experiment, because by definition it requires you to sort of prepare the state you want, which if you've done that, you don't need control anymore. But it was a really nice method because it's more deterministic. There's not this like intrinsic randomness that the genetic algorithm has, but like it also, like I got a lot more results a lot faster. We could implement things like bandwidth constraints and whatnot, and so like that was really very cool. And so a lot of that work underpinned a lot of what we did in the experiment, even if it wasn't directly relevant. My model wasn't good enough to directly implement in the experiment, and so this is something that I tend to sort of press on collaborators is, how good is your model relative to the experiment? Folks that followed on from me in Boulder, I think made the model a lot better.
So I just wanted to mention here something that I absolutely loved about Carrie's thesis. And this is that it was written in a way that was extremely readable and with the PhD students that came after her explicitly in mind. So I talked to her a little bit more about this. There's not enough time to include all the detail in this episode, but the team at Boulder have carried out a bunch of work following on from her PhD since, so collecting more data, improving the characterization of the system, and combining more standard optimization approaches with machine learning.
So that's Krotov. And then this CRAB algorithm was it stands for constrained random basis optimization. And all it really corresponds to is that you take the control you want and you decompose it in some basis. Doesn't really matter what it is. CRAB will work regardless. I use the Fourier basis because I like to think in frequencies. You could use wavelets, you could use, Heaviside, functions, whatever you wanted, and you could decompose it. And actually, one of my collaborators in Vienna was looking at like the role of bases and like finding optima because it changes the landscape. It's very interesting work. It's super cool. Her name's Fila Rimbold. She does very cool work.
So the paper that came out of this work by Fila Rimbold is titled "The Role of Bases in Quantum Optimal Control." And it looked at the use of 3 different bases with the crab optimization, applying this to different problems. So the bases they used were Fourier, sinc, so sin x over x, and sigmoid. And they found that the bases used had a massive impact on the convergence rate of the optimization, but that you needed to match the bases that you used to the particular problem. There was also a super interesting comment at the end of the article, hypothesizing about whether you could get better performance by combining these bases, either sequentially or creating kind of hybrid bases.
And then what you have to do is you sort of decompose your control into what, this basis, but then you need an optimization method. You could actually throw that into the genetic algorithm and it would work just fine. But it was this Nelder-Mead optimizer, which is this kind of like amoeba simplex method where you sample your search space and then based on the like collective of all of your samples and like how they lie geometrically, you sort of manipulate this set of vertices such that you eventually kind of worm your way into an optimum. And, it's important to actually mention that like it's very difficult to say, yes, this is a global optimum. This is, the best I could possibly do in the shortest amount of time. That's like extraordinarily difficult to prove analytically in most cases. Usually we're just like, that's good enough. And so I became a champion of good enough.
I wanted to add a little bit more detail on Nelder-Mead here, just in case anyone currently has an optimization problem and is on the lookout for potential approaches to solving it. So this is an algorithm used to find local optimum of an objective function in multidimensional space, and it can be applied to nonlinear problems where the derivatives aren't known. It often gets satisfactory results very quickly, but at least according to the article I was reading, it doesn't have guaranteed convergence results, except for when applied to very specific types of problems.
But one of the nice things about the crab algorithm is that it would work fairly well even with something like 5 vertices, whereas in the genetic algorithm I was throwing like 200 genomes at the compute cluster. And 5 was enough that I could implement it experimentally. So actually the experimental results that we got were just like the crab algorithm working and on 5 genomes. And what I would do is I get the experiment going so that it would run itself, which was a lot of fun and not all that trivial. And so I'd hit go and then I'd like go off and do something and come back a couple hours later. And if everything, all my lasers were happy and whatnot, it would work sometimes, but it wouldn't work other times. And actually figuring out what the difference was between when it worked and when it didn't work led to like an understanding of the underlying physics behind the system. So that was really interesting.
So you mentioned the fact that you can't get a global optimum. I know in your PhD there was like a variation on crab called dress crab that I think kind of tried to get around that somewhat.
Yeah, I think the same thing happened where like you can't guarantee that what you found was the best, but you can get to like a plateau where crab is like, cool, we're done, like we're making very small changes, like good luck. And you'd be like, well, that answer kind of sucks. And you'd be like, what do I do? And then dress crab would like come in and save the day. And what it would basically do is it would like re-roll your basis. So what you did in crab, if you think about the Fourier basis, is you didn't want to have like 1 hertz, 2 hertz, 3 hertz, 4 hertz, 5 hertz, all the way up to like 100 kilohertz. You'd kind of randomly pick, 5 or 6 frequencies in this span. And sometimes they wouldn't be the right frequencies. And actually that gets at the sort of, understanding what frequencies were good and what frequencies were bad actually was related to the underlying physics of the problem. We actually kind of did this backwards. I should have done the physics first and then the control, but that's neither here nor there. And so what dress crab would do is it would say, the 6 frequencies you chose were all terrible. Let's choose 6 more frequencies. And so it would take the control that you found. It wouldn't like throw all the work that you'd done, into the bin. It would take the control that you found and then it would sort of reshape the landscape. And then, it would redo this Nelder-Mead optimization. And then you kind of climb farther up the mountain. And then it would do it again and again and again. And so actually we ended up implementing this in the experiment where it would go. And you'd see it kind of jump every time it re-rolled. In a good way, it would jump. Like sometimes it would kind of stay where it was and you'd be like, yay, it did nothing. But yeah, that was the whole idea of dressed crab, was kind of, re-rolling your stats every time you realized they were terrible.
So I know you wrote a review paper earlier this year on kind of robust control of quantum systems. I think my plan was kind of use that to give an overview of the topic before diving into some of the more detail. Okay, so just kind of background, general quantum concepts. My first question was going to be on kind of the notion of a state in quantum systems.
Yeah.
And how that relates to the traditional control notion of state.
Yeah, so, and you'll have to forgive me if I get any of the control language wrong. The review paper is kind of interesting because we started work on that in 2019. And it was myself and a few other people from various groups in the States, and then lectures were given and everybody gave a talk. And it was really very, very cool. And we decided, well, let's, funding agencies like it when you do something and something practical comes out of it. So we said, well, let's write this survey review paper. We wrote it, and it was kind of one of those where they're like, okay, where do we put it? Figure out where you're going to put a review paper before you write the review paper. A lot of topics need invitations and things like that. So we learned that the hard way. So thinking about that, what's the concept of a state? So if you think about what a state is in control, it's usually kind of at least with my experimentalist brain, it's kind of a set of characteristics of the system, right? Usually you can measure those characteristics. I mean, perhaps not entirely, but and then the concept of feedback kind of gets into the concept of are you actually making the measurement, or have you just sort of hooked up a wire from point A to point B? And in a sense, a quantum state is very much the same thing. It's a set of characteristics about a system that in principle you could measure. In practice, it could be rather difficult to measure. You'll have people in quantum computing talking about things like state tomography, and that's the complex set of measurements that you have to make to get all of the full information about your state. And actually in the experiment for the lattice stuff, and actually most of the experiments that I do, it's very difficult to get full information about the state.
Now, if, like me, you're from a more classical control background, you may be listening to this thinking, hang on a second, couldn't you just fix this problem using an observer? So I went on a bit of a journey through quantum observer design, and this is very cool. So the quantum analog to a Kalman filter is something called a Belavkin-Carmichael quantum filter. I did go back and look at the original paper, but it gets very mathsy very quickly, so I did get a bit lost. But people have also extended the traditional Leuenberger filter to quantum systems, and I found two really interesting CDC papers that were a lot more accessible. And it turns out that the fact that the system is quantum causes issues for traditional controller observer architecture, because you can't just measure the outputs and then feed that into an observer, because this destroys the quantum state. So these papers instead propose using an observer that is itself an inherently quantum system, and then using beam splitting to get around the measurement issue, which is very cool.
And so that there are a lot of interesting things about quantum control that kind of derive from that notion. And in addition, the equations that drive the equations of motion for these states are usually bilinear instead of being linear. I'm not a control expert. All I can tell you is that my control expert friends just talk about how much of a pain that makes things. A lot of the machinery of classical control is difficult to implement in that type of system. And then not even to mention the fact that some people look at, non-Markovian systems. I never have. They're terrifying. But the idea that a system can have memory, everything goes out the window. I tend to like systems where you look at it in time t and you look at its equation of motion, you say, that's how it's going to go, as opposed to having to look at t and t minus tau and, whatnot.
So I went and looked into this, and I came across a few super interesting papers examining the control of non-Markovian quantum systems. So the general idea is that in certain situations, the environment has some memory related to the decoherence of the system, and this can be exploited to restore the system's coherence. And some people have tackled this using machine learning and data-driven approaches, but you can also model the systems using quantum stochastic differential equations, and then use more traditional optimization-based approach.
So your review paper focused on both closed and open quantum systems. Mm-hmm. So what are the differences between these, and how does this impact your ability to control them?
Yeah, so one thing to mention is that in terms of the control of open quantum systems, for folks that are interested, there's a really nice paper And actually, I think even like set of papers by Christiane Koch, who's a professor in Berlin. And she's just, one of the giants of quantum control, in my opinion. And so I think her work really focuses in on, what it is to control an open quantum system.
So I've linked below the review paper that Christiana wrote on this topic, which gives a really great overview of a lot of the things that we're mentioning in this episode, as well as topics that I'm planning to discuss with Sophie Shermer in the next episode. Also, the concept of unitary evolution is about to be mentioned, and I figured possibly not everyone listening would know what that means. So Carrie will explain what this means from a quantum physics perspective, but mathematically, a unitary operator is an operator that preserves the inner product. So if you multiply two vectors by the same unitary matrix, the distance between them won't change.
But one of the interesting things is a closed quantum system will evolve unitarily. If you actually take the Hamiltonian that describes the dynamics of the system, and you look at its eigenvalues, they're all entirely real. But then actually the evolution of the system will actually go as, there's an imaginary factor out front. Actually, unitary evolution is often described as the exponential of I times the Hamiltonian times time. And so as a result, if you actually think about the dynamics of the system, they tend to be, in many ways, oscillatory. And if you look at things, I really love this analogy. It only goes so far, but I really love it. If you look at the pole zero plot, and you look at the eigenvalues of this Hamiltonian, then multiplied by this imaginary factor, they all lie on the imaginary axis. So the system actually has no real stability to think of. One of the fun things about open quantum systems is then that adds in dissipation. It must. Like if you add in sort of anti-dissipation, you've now got something that you can drive off to infinity. This is going to actually push your poles into the left half of the real plane in most cases. And so open quantum systems sort of take your regular kind of Hamiltonian unitary dynamics that are very, very nice and described by the Schrödinger equation to this kind of irregular, it does make the Markovian approximation, and there are many, 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 many ways to describe open quantum systems. But you've got sort of the unitary part that evolves very, very nicely, and then you've got this part where there's not an I out front, like things start to dissipate. And I love to teach this. This is one of my favorite things to teach, because one of the games that you play is you try to figure out what the dissipators are. Like, what are the mathematical terms that you can use to accurately describe, like, the system losing its phase, the system, losing its coherence, the decoherence, dephasing, and other sort of dissipative mechanisms, like, you're losing excitations in the system or something like that. This doesn't really map nicely to the lattice problem. Like, it actually, you see this a lot with people describing things like qubits or qubits or like finite dimensional systems that you either can't or don't describe in like the sort of nice continuous momentum versus position picture, but rather you write down this concept of a density matrix that describes not only the population that you have in each of your quantum states that you can measure, but actually also maps out like coherences between them, which are very uniquely quantum and, really give quantum mechanics its kind of power and utility and all the fun stuff.
To summarize very quickly, closed systems evolve unitarily, whilst open systems have dissipation, and this dissipation leads to decoherence of the system.
Now, controlling closed quantum systems, i.e. not open, is relatively straightforward because of this unitary behavior. But controlling open quantum systems, because you have this dissipation, you have to ask the question of, can I get from the state I start in to the state I want? Or if I'm doing, say, unitary optimization, gate optimization, where I don't actually care, what state I start in, what state I end with, but I want the same operation to happen regardless. And this is really useful for quantum computing because they design things like gates and whatnot. Like, can you even do this, with the various sources of noise that come in?
So I guess you mentioned kind of quantum gates already, because my next question was going to be about kind of examples and applications of quantum control. Because I know in your papers you've got a few examples, but not necessarily like physical systems.
Yeah, and that is one of the things is that quantum mechanics is very hard to solve analytically, except in like fairly simple cases. But when you're developing theories and you're developing, you're applying these things, you tend to go back to those simple systems because you just want to show that what you're doing does what you think it should. And one of the questions, I'm a really annoying reviewer for quantum control papers, because one of the questions I always ask is sort of scalability to larger systems. People will say, I'm going to look at a 2-dimensional, 3-dimensional system. And I say, yes, but what if you have, instead of 1 qubit, what if you have 2 or 3? And they're like, please stop. But one of the nice things is that like all of these kind of, I say quote unquote contrived systems aren't actually contrived. Like they're rooted in something. And usually if you say, yes, I have a model of spins that interact in this way, you can think, okay, what is that useful for? Well, sometimes it's useful for information transfer or quantum memory, sort of the storage of quantum information. But you can also think about the ubiquitous qubit and sets of qubits that make up quantum computers that, in principle, with enough qubits could kind of do whatever quantum calculation you wanted. And people get really excited about this for various reasons. And then, there's always the application of wanting to control a real system. And then that's often where the devil lies in the details. And so we have a fairly recent paper. Actually, we've started to think more and more about if we have atoms in a lattice and we shine a laser on it, how does that affect how we can control the atoms? Oh, but by the way, we can't have an infinitely precise laser with infinite power. What if we actually put in realistic experimental constraints? And that makes my theorist colleagues cry, but then they come up with really cool results and we write papers about it.
Okay, so in terms of kind of robust quantum control generally, you might have mentioned a few reasons already, but what are the challenges when controlling quantum systems, particularly designing robust quantum controllers?
Yeah, that's a really good question. And there's been a lot of work in designing robust quantum controllers. And the question is always kind of robustness to what? And it's usually robustness to, say, the environmental noises and decoherences and whatnot that I discussed when discussing open quantum systems. Like the things in the environment around us that we can't really control. Sometimes this is like stray electromagnetic fields, for example. Like the room that you and I are sitting in, we're not being, actively microwaved as we're sitting in here, otherwise it'd get rather warm. But that type of electromagnetic radiation that's all the way around us, like it actually can really hurt quantum systems that you're trying to control. So people are both trying to mitigate that, but then also design ways to control these systems that take that into account. But then there's also the concept of here's the stuff that we're actively doing, like the lasers, for me it's, lasers and atoms is always what I think about, but like the drives that you are actually applying, the microwave drives that you're using for your transmon qubit, the lasers that I'm shooting at my atoms, these types of things, how much and how fast am I shaking things around with my lovely shaken lattice? The question then becomes, what's the noise in that? And how much is that going to be a problem? And so you want to design controls that are robust to that. But then there's also the question of quantum sensing. Like, what if I want to sense an electromagnetic field, right? I actually want then to design a control that's robust to everything but the thing I want to sense. I want it to actually be minimally robust to that. And these questions, I think, I find very, very interesting. And classical robust control theory really does seem to only go so far. We have a paper where we looked at kind of this idea of mu analysis, and we did come up with a system where we could look at it, but it was a very specific subset of problems that you could apply in this way.
So the paper that Carrie's mentioning here was titled Applying Classical Control Techniques to Quantum Systems, Entanglement versus Stability Margin and Other Limitations. And they define the concept of a transfer function for quantum systems and then use this to examine the impact of various perturbations. However, the paper found that for the system they considered, this classically inspired stability margin was only a useful metric for very particular types of structured perturbations, and also found that this depended on what performance metric you were actually looking at.
And there are a lot of researchers that have looked at very, very cool problems, but you have to think about kind of the regime of applicability of your, robust control design. I am thinking of a paper recently by a researcher, so this is Randa Herzala, who basically they derived a robust control framework, assuming sort of Gaussian noise in the environment and in the state. And so that applies in a number of cases, but there are cases where it won't. And so what we've actually started looking at is, given a controller that you found in one way, shape, or form, you beat it with the optimization hammer until it, finally gave you 1 or 10 or 500 controllers that you like. now you want to evaluate the robustness of those controllers. What types of tools can you use? And so a number of the papers that we've written in recent years have developed these tools and then applied them. Because I always say to my collaborators, I say, what I really only care about is having one control that works, and that works really well. So if you say, here's 500 and here are their characteristics, well, we have to figure out what the best of those 500 is. And sometimes the best controller, it really depends on what you want to do with it.
This is like less related to robustness, and then I might come back. But you mentioned in your survey paper the compromise for quantum systems in terms of stability and quantum advantage. So can you talk a bit about that?
Yeah, I don't know that we can make any absolute statements about sort of a system retaining its quantumness versus what would allow a system to be stable in the classical sense. So if you think about, again, our unitary system with the poles lying on the imaginary axis, technically marginally stable, but actually in a quantum mechanical sense, as long as it's going to continue behaving unitarily, that kind of just does its thing, right? But then if you think about, now I'm going to add some dissipation and I'm going to move my poles into the left half of the imaginary plane, this then provides some stability from a classical standpoint, right? You have this stability margin. Naively, one could even think about it as a distance from your kind of closest pole to the imaginary axis to the axis itself. But of course, the more you drive your system into that left half of the plane, the more decoherence and dephasing and all of the nasty stuff happens. And so you start to really kind of lose that quantum character of your system. I was actually just at a conference on quantum thermodynamics, and so there's lots of concepts of useful work and resources and utility that you can get out of these systems.
I did a little bit of research into control in the context of quantum thermodynamics, and from the few papers that I looked at, this just seemed really cool. So one of the papers I was looking at was trying to answer the question of how to best control a quantum heat engine by modulating how the quantum system interacted with two different heat baths of different temperatures. And the researchers found that the optimal solution was essentially bang-bang control, and they looked at kind of necessary conditions that needed to be satisfied at the point where the control was switched.
And so that kind of leads to the concept of actually thinking about new ways to think about robustness in a quantum sense. Can you take a system that's classically marginally stable, but actually define notions of quantum robustness? Because the quantum system itself, if it's evolving unitarily, doesn't care about classical stability, but you can have kind of more and less robust controllers, right? Let's say we're going from state A to state B, and we look at the fidelity with respect to state B, basically how close my state at a given time is to state B, and I have a controller that very nicely and smoothly goes to state B, and almost seems like it plateaus before it goes to state B. You can think of, that one might be more robust. If I stop my controller a little bit too soon or a little bit too late, it's probably going to be pretty close to state B. Or if I have a little bit of a perturbation, it's going to get kind of close. But if I have one where it stays really, really close to state A or to any other state in the system, and then all of a sudden at the very end it pops up and now it's in state B, I'm very, very happy. But what if I, don't stop my controller at that specific time, right? It's going to be way off. And so those are the types of things that you think about when you think about this quantum robustness. And so I think it's a very open question and an interesting one about just how far does classical control theory go? I think physicists and control theorists are often solving the same problem in two different ways, and maybe we need to talk a bit more. But it's hard because the language is different.
Okay, so in terms of kind of trade-offs, a few of the papers mention the ability of coherent quantum systems to exhibit both small error and small logarithmic sensitivity.
Yeah.
Could you explain a bit about that? Because you wouldn't necessarily expect that.
Yeah, there's this classical notion of a robustness fidelity trade-off. And this is, I think, something that I don't think there's anything in quantum mechanics that says that you can't have a high fidelity and robust solution. And we've looked at a number of different systems. I'm actually thinking about one that we're looking at now, where actually it seems like there's a little bit of a robustness fidelity trade-off. We can find a solution that's quite good. Say it's 99.9% close to the state that we want, and that one is actually going to be more robust than one that's 99.99999% close to the state we want. And Sophie Shermer, who's doing all the optimization, is able to find these crazy high fidelity controls, and we are finding that those tend to be the least robust ones. But we've also found problems where this trade-off doesn't seem to be the case, that we can actually have very nice, good fidelity controllers that are fairly robust. Like, there just seem to be, in a lot of cases, like kind of golden controllers that do what you want and seem to do it in a fairly robust way. And so it seems to be both problem dependent and method of evaluating robustness dependent. I'm not sure there are going to be absolute statements that can ever be made about this kind of robustness fidelity trade-off. And I think that's really, really interesting.
Because there was an interesting paper that you were involved in on kind of defining a single measure for robustness and fidelity. Can you talk a bit about that? Yeah,
there's this, we called it the robustness infidelity measure. This was coined by the PhD student on the project, Irtaza Khalid, who's now doing a postdoc in Cardiff on like natural language processing or something, cool like that. And what Irtaza basically was looking at was a way of quantifying, as you said, both fidelity and robustness kind of with one number. And so he came up with this concept of a RIM, which was a robustness and fidelity measure, which was kind of, you took your system and you sampled it with a whole bunch of different perturbations, right? You have your controller, you've optimized it in the most ideal case, and now you start to perturb your system and you look at how the fidelity of that controller changes. A perfectly robust controller will just stay at unit fidelity regardless of how much you sample it, right? There's the ideal distribution, which is actually just a delta function at 1. And you're like, cool, great, that's not a distribution. And all the mathematicians go cry and the physicists go, what's the issue? Cares that you can't differentiate it or integrate it or that it's continuous. But in reality, you're going to get some distribution. And what the RIM actually does is it computes the Wasserstein distance between the distribution you get and the distribution you want, right? This ideal delta function-esque distribution. And then there were basically like higher order ways of looking at this that I kind of emphasized the tails more of these distributions. And what Irtaza actually found was that the first order RIM, which was just the average fidelity, was good enough. So actually, at least for the system that we looked at, a controller with a high average fidelity, as you sampled, was going to be the most robust controller. Like all the other kind of higher order robustness and fidelity measures were kind of bounded from above by this one that just decomposed to, let's poke the system a whole bunch and then take the average fidelity. And I really, really like that paper because it's kind of just intuitive in that regard. And he put a lot of rigor into kind of figuring this out and understanding it. And we looked at it for a number of different systems and published some very, very cool results.
I would like to say that I did also really enjoy reading this paper and found it to be very accessible for people without a quantum physics background.
Now, it does require you to sample. And so this concept of the logarithmic sensitivity or taking derivatives of the fidelity with respect to some parameter, in principle, you don't have to sample to get that. Or if you do, you sample a few times to take a nice numerical derivative or something like that. And so if you can sample, great, do so. Which is often what you want to do if you have, say, a time-dependent perturbation or some more complex perturbation that isn't just like straightforward to sit there and, do derivatives about it all day. But the log sensitivity was one that was nice because it was kind of a one-shot method. And then there's a paper actually that Sean O'Neill, who is the log sensitivity guru, and Irtaza, who is the RIM guru, they actually came together and they showed that there is a link between the two, which in many ways my part in these papers, I'll be perfectly honest, is to kind of go, oh yes, this is very cool. How is it useful in real situations, and they're like, I don't know, Carrie, you figure it out and write a few paragraphs. And I'm like, will do, But I've been really, really lucky and really fortunate to work with these guys because they're extraordinarily just clever and nice, and that's what you want in a collaborator, somebody that's not a jerk and knows a lot more than you do about certain things.
Just adding a little more detail here because I found this really, really interesting. So, as you may already know, sensitivity in control theory is traditionally formulated in the frequency domain, and there's a well-known identity that says that the tracking error plus the sensitivity must be equal to 1. However, this frequency domain characterization isn't always super useful for quantum systems in which there may be particular constraints or specifications in the time domain. So there was a paper that Carrie was involved in that proposed a measure of log sensitivity that could be applied to time domain signals instead. So in this paper, they showed that their proposed log sensitivity measure diverges as the system approaches the desired steady state error, which is exactly the sort of trade-off that you would expect from the frequency domain characterization. Now, the paper that Carrie mentioned here looks at the link between this time domain sensitivity and the RIM, and they found that there's a very neat link between them via the differential sensitivity of the system, so how the error changes for small changes in perturbation strength. I've linked both those papers in the description. They're very interesting.
Okay, so kind of going back to robust analysis in quantum systems. So you worked on a few different papers. So you mentioned mu analysis and structured singular value analysis. So why are these approaches useful for analysing quantum systems, and what are the challenges faced when trying to apply them?
Yeah. This one's definitely not in my wheelhouse, but let me give it a shot. What we found is that this mu analysis did require an open quantum system of sorts. You couldn't analyze unitary behavior in this regard. Basically, from what we could understand, there's only a certain class of problems that you could apply this sort of mu analysis. And I don't claim that we sort of exhaustively solved the problem. I think that there's still something there. Because these concepts of sort of structured singular values and you know, principal components, for example, like these are problems I continue to poke at. But it seemed like there were certain constraints on the system. And so when you take the constraints on the system that you needed to apply these mu analyses, it's difficult to apply this to kind of real world applicable problems. Like, it was very difficult to say, yes, we could do this, and then we could compare it to this experiment or something along those lines. But I will couch that in saying that we haven't been exhaustive here. I know it remains in the back of mostly my collaborators' heads, but also my own, because there is so much on classical robust control theory, right? You know, people have written multitudes of textbooks about it, and I often make the joke that my collaborators have their black belts in linear algebra, and I'm just sort of stumbling into the room, you know, with the physicists that, you know, probably can't even tie their belt correctly type of thing. So, yeah.
So, the last kind of technical section, I wanted to discuss the work you've done on energy landscape shaping. So you published a paper earlier this year that presents this as an alternative to conventional dynamic control.
Yeah, and I will say that, like, energy landscape shaping, like, when it can give you an answer is really, really cool. Dynamic control is usually going to be faster, but it's also going to be oftentimes a bit more difficult in an experiment. What energy landscape shaping is, the way I like to explain it is, you have your system, and it's got some set of eigenvalues, eigenvectors, whatnot. And now we're going to, like, perturb the system a little bit. And we have the state that we start in and the state that we want. And if we start in an eigenstate of my kind of unperturbed system, all that's going to happen is it's just going to stay there, right? So if I want to drive from one eigenstate to another, what I have to do is I have to perturb the system in some way. So let's say, like, we can think of like a network of coupled spins. If I excite, say, one on the left and I want it to go over to one on the right, and there's, you know, some number of spins in between, well, if I don't do anything to that system, it's mostly just going to kind of hang out. So what I have to do is I have to perturb my system in some way. I might have to change the couplings between the different spins, or I might have to, you know, change something about how they interact together. And then what I do is I don't drive it dynamically. I don't actually change that perturbation. I just set it up and I say, go. And then it just goes. And eventually, maybe my leftmost spin has gone over to my rightmost spin. I figure out when that happens, and I say, okay, stop. And I turn off my perturbation, and lo and behold, I've done what I want. And this is really, really cool because it doesn't require you to have dynamics. One of the papers that we published fairly recently looked at actually coupled spins as atoms sitting in one of these optical lattices. And the way we controlled those couplings was we shone a laser field on them. And we actually, the hard bit was that we took into account the fact that the laser can't be like infinitely narrow. It has some space to it so there was always a leakage between sites. I'd shine a laser on one site and it would sort of hit site 2, site 3, or, you know, that there was a finite amount of power that we could put into the system, things like that. And so what we then did is you could shine on that light field and you didn't have to change it. You could just shine it on, which is fairly easy. You let it evolve, which is fairly easy, and you turn it off at some time, which is, you know, fairly easy. And so that's one of the things that's nice about energy landscape control. Now, dynamic control, you know, most of what I do is actually dynamic control. I love them both, but they have advantages in different ways. There are going to be problems where dynamic control is going to be far more suitable than static energy landscape control, and vice versa.
Can you give like examples of which you should use?
That's a really good one. I think for the spins, I think the static control is going to be, especially in terms of robustness, I feel like that would be far more robust. But again, I might be wrong there. I think it's going to depend on your actual experimental implementation. The way I would say it is like use dynamics if you can. If you can't, think about, you know, this sort of static control.
Okay, so the paper formulates a hybrid optimization with both continuous and discrete control parameters. Mm-hmm. So why is that kind of useful or necessary?
Yeah. So useful, I think the utility is that, like, I think this pops up more than people care to admit. But the reason why we needed it is that it was the specific implementation.
So Carrie's about to explain the experimental background behind this, which is super cool. But if you are a controls person itching for more detail on the optimization, rest assured that I'm very much planning to dive into this in next month's episode with Sophie Schirmer. But for the time being, enjoy the experimental info.
We shone a laser field onto, you know, basically a bunch of atoms sitting like eggs in an egg carton, right? But the way we shone that laser field is we actually reflected it in our model. And this is actually related to an experiment that I worked on while I was a postdoc at Aarhus University. In Jakob Scherson's group, and it was a laser beam that was reflecting off of a mirror and then onto the atoms. But the way we controlled the shape of the laser beam was the mirror was actually a digital mirror device. So it was a set of pixels. They were like little MEMS mirrors that you could either point one way or the other. So instead of one mirror, it was like 1,000 by 2,000 pixels that you could individually control. These are awesome devices. I have some in my lab now, but it's a binary pattern, right? So the light's either going up or it's going off at some weird angle that we then ignore and block so that it doesn't shine in people's eyes and whatnot. But then our pixels, that was also very discrete. So this was discrete. But my laser itself, I can more or less continuously change its power, right? Like it literally is a knob that I turn and you can see the power in this projected potential go up and down continuously. So in order to hit that, we had to have this discrete continuous optimization algorithm that Sophie Schirmer came up with. She's the last author on the paper. And it worked. Like, I mean, I think she tried a few things. And then she was like, yeah, I did this kind of combined discrete continuous optimization, and lo and behold, you know, here are something like 25 controllers that do the job, and one of them was ill-behaved. And then we evaluated them, and I think one of the last sets of paragraphs in the paper is like, okay, if we wanted to do this in a real system, we'd take, you know, this controller, or this controller, and those are the ones that we would try first. And so, yeah, that's where it popped up. I think Sophie's really proud of this this method that she came up with, kind of rightfully so, because like I said, I think it's going to find utility outside of this specific kind of odd edge case that we were using.
Okay, so I've got some kind of more general questions about quantum control.
Cool.
And then like quick questions. So, where do you think quantum control is headed in future?
I think you're going to see a lot more people looking at real systems and their control, but then also how good those controls are as you take the technology out of the lab and into the real world. I think this is kind of the natural consequence of the quantum technologies being so focused on. Do I think that quantum technology should be focused on? Yes, absolutely. I would like to say that we shouldn't ignore kind of the quantum science of things, the science of, you know, understanding these various models and these, you know, these various things that aren't perhaps immediately applicable to building a quantum computer or a quantum sensor, you know, that sort of thing. But I think that you're going to get increasing focus on quantum control for practical purposes.
What do you think are the biggest challenges that need to be overcome to make progress in quantum control? And are there inherent limitations on quantum systems, or do we just need better control strategies?
So I think one of the biggest challenges that we face in terms of advancing the field of quantum control, I think, is actually human. You have control theorists, you have quantum physicists, and then you have, all the other people that are looking at this. And kind of, it almost seems like the Venn diagram of people working on this in the various different fields is 3 circles, whereas really we need to come together and we need to talk more. But of course it's very difficult because the language is different, and I think you're getting a lot of duplication of work, and that, we should try to come together more. But I also recognize that is extraordinarily challenging, right? People like to kind of just do their own thing, and if somebody comes in and they said, we did that 20 years ago, you're like, oh, that's nice. We did it with lasers, But then I think one of the things with quantum technologies that is very interesting is that quantum technologies are useful, but they're also kind of intrinsically fragile. There are a lot of people looking at what are the effects of the environment. I was at this conference last week of quantum thermodynamics. What are the intrinsic energy costs of erasing a qubit? All of these very, very cool, but also very, very fundamental questions. And I think that one of the biggest fundamental issues is that we are classical beings, right? We're big and squishy and kind of gross, and quantum devices, often have to be very cold. They have to be kept in very quiet places. They have to be shielded from black body radiation, right? But we have to talk to it, right? We have to get something useful out at the end. And every time we talk to it, we either destroy it completely or we perturb it. And so understanding what the limitations of the fact that, quantum devices are still in the world that we also inhabit, is I think one of the really interesting things that we'll have to figure out. Better controls will always help us. I think I'm firmly in that opinion. And it's very difficult to kind of, do a derivation to figure out just how bad a quantum computer is intrinsically. Although there's some really interesting work in that regard. David DiFincenzo has done a lot of work looking at or underlying things that we can't control going to kill, superconducting qubits or, something along those lines. And I think we actually don't know, but we'll find out.
What are you most excited about in the future of quantum systems?
Oh man, I'm just excited to see where the technology goes and what technologies come out of it. I'm not sure we'll ever build a fault-tolerant quantum computer. But I say that, tons of engineering has gone into it, and tons of science has gone into it, and people are making enormous leaps and bounds, and there's so much money being poured into it also. But there's also quantum sensing, where they're putting quantum sensors on airplanes and, mapping out the Earth's magnetic field and using that to figure out where you are, right? And that has a lot of implications, both for environmental sensing, but also geopolitical implications because of GPS denied navigation and things like that. And I think I think quantum sensing is probably the technology that's closest to moving out of the lab. But the technologies that we develop as we develop all this is going to kind of feed back into the broader world. You need, say, a better RF amplifier to control your qubit better. Well, that RF amplifier can be used in loads of different fields. There's actually quite a bit of societal benefit that I think can come out of this.
Okay, so kind of final quickfire questions. What's the best piece of advice you've ever received?
Ooh, that is a really good one. I think one of the best pieces of advice that I've received, this came from a buddy of mine, and I don't think the quote, I think she got it from somewhere, but it said be who you are, and basically be your authentic self, because the people that mind that you are who you are, they don't matter, and the people that matter won't mind, and that sort of, most of us that work in this field, we're to some degree march to the beat of our own drummer. And that is totally okay. But it also, it really helps both me understand that, it's okay to be a little bit quirky, but also, the students and the people that I work with are going to have similar quirks. And you have to kind of, I really think that inclusivity in this field is really paramount. because the more you get a diversity of thought and opinion from people with a diversity of sort of lived cultural, socioeconomic, whatever experiences, I think you're going to get a better output because you're going to have so much feedback from so many different types of folk. And so that's one of the things that I think is, to sort of, it's okay to be your authentic self, with the caveat that if your authentic self is a jerk, maybe don't be a jerk.
What's your favourite part of your job?
My favorite part of my job, like fundamentally, is the fact that like so many of the people and the students and whatnot that I work with are just so clever and so like all kind of in their own unique ways, right? There's not like kind of one mold of student that just sort of, they cloned and they popped out. Like everybody's got their own unique advantages, strengths, but also weaknesses and challenges. And one of my favorite parts of my job is when somebody who perhaps was struggling in one way, shape, or form, then like kind of blossoms and turns on and really like finds their space. And everybody that I've worked with has that. I very rarely run into somebody that's truly lazy for the sake of being lazy, right? They usually have something that they're struggling with. Or somebody that like is truly like just truly doesn't get it. Like there's something that they can do at a truly world-class level. And so kind of finding that and nurturing that while also like shoring up weaknesses and whatnot, that's one of my favorite parts of the job.
Who's your role model within the field of either robust control or quantum physics?
That's also a really good question. Actually, like one of my role models, and like I try not to put people on pedestals because we're flawed, right? Like Erwin Schrödinger was a very, very troubled individual that did not make the best decisions, and likewise, like the people can levy criticism against Feynman, against all sorts of things, right? We're all human and flawed. But one of the physicists that I routinely drew inspiration from as I was kind of growing up was Enrico Fermi, because he was one of the best physicists that ever lived, but also he was a great theorist and a great experimentalist. And I always really looked upon that as kind of you don't have to pigeonhole yourself. And so I really appreciate that.
Final question, what's been your favourite paper or project to have worked on?
I'd say the paper I'm most proud of is I have a 2-author paper, myself and my PhD advisor, in Physical Review Letters, which is one of the kind of bigger journals in my field. And that one I'm just proud of because we did it. that was really cool. But one of my favorite papers, I had some collaborators that at the time were in Bonn, but this idea of sort of looking at a picture of an atom and modifying sort of its point spread function, its impulse response function, the pinprick dot of light as it moves through your optical system, and then you record it on a camera, and actually modifying that with this device really similar to the digital mirror device, so that we could actually figure out where it was in all 3 dimensions. Whereas it's really hard to get information kind of moving into and out of the focal plane with the same precision that you can moving left and right. And again, the first author on that paper is a master's student who's now a PhD student in Bonn. And his efforts were heroic to not only get the experimental data, because the lab literally shut down the day we finished. And actually we couldn't take more data even if we wanted to, because people were sort of pounding on the door. And he was in there just finishing up data sets and data sets and data sets and doing tons of analysis and then doing all of this in his quote unquote spare time as he's trying to be a PhD student, and just I'm really proud of that work.
Okay, that's all my questions. Thank you so much for the interview.
Yeah, no, thank you.
So, in summary, quantum control generally involves moving a system from the ground state to some target state in some finite time. This problem is often hard to solve analytically, so optimization approaches such as Krotov's method and the crab method are often used instead. Closed quantum systems evolve unitarily, which results in them being oscillatory and hard to apply classical notions of stability and robustness to. In contrast, open systems have dissipation, but this means that it might no longer be possible to get to the state that you want to. The fidelity of a quantum system is a useful performance metric, and the RIM gives a way of quantifying both fidelity and robustness. Finally, Energy landscape shaping gives an alternative to dynamic control and involves altering the Hamiltonian of the system and letting it naturally evolve to reach the desired state. I really hope you've enjoyed this episode. I've had so much fun finding out about quantum systems and quantum control, which is why I've decided to continue that with a follow-on episode. If you did like it, please feel free to subscribe to the podcast. You can also follow both me and the podcast on LinkedIn. So, as you're all very much aware by now, next month's episode is going to be with Sophie Shermer. At the time of editing, I haven't recorded that yet, but I'm very much looking forward to it. I am currently in the depths of researching very interesting maths behind quantum control, topics such as controllability, various different control paradigms. It's going to be great. Plan is to release that on the 1st of December, but until then, I hope you have a fabulous month.